from what we saw in the preceding then, this basis, which I'll call B prime, consisting of the 0.6, 0.8, and the 0.8, negative 0.6 vectors, is an orthonormal basis for R2. Okay, these vectors are linearly independent. Their dot product is 0. Their magnitudes are 1. You have two linearly independent vectors in R2. They span R2. The dimension of R2 is 2. So any two linearly independent vectors span, but it's particularly convenient to have unit vectors that are orthogonal to one another. And of course, that's just what we have, for example, if we have our I, J vectors spanning R2. But this is an equally good set of vectors to span R2. Okay. So, let's now look at this set. Okay, this set is linearly independent. Okay, you can easily prove that, and we know how to prove that. So it's a basis for R2, because it's two vectors in R2 constitutes a basis. But the dot product of these two vectors is not 0. What do we have? We have 6 and 12, which is 18. That's certainly not 0. These are not orthogonal. What are we going to do about this? Well, here we have a picture. Okay, we have the vector v2, the vector v1. Okay, call this v2, call this v1. Doesn't matter. Anytime you have two vectors, you can project one vector onto the other. Sometimes I'll project v1 on v2, sometimes I'll project v2 on v1. It doesn't really matter. The projection of v1 on v2 is what? Well, this right triangle here has a leg that's equal to the scalar projection of v1 on v2. That just means we go from the tip of v2 down to v1 at a right angle. Now, more detail, we've done this before, we've seen this before, so in a subsequent video I think I will actually go into a little more detail on this. Now, here we have the v2 vector. The v2 vector divided by its magnitude is a unit vector, so this little blue arrow represents a unit vector in the direction of v2. We multiply that by the length of this purple line, which is the scalar projection, and now we have this orange vector, which is the component of the v1 vector in the direction of v2. It's it's the part of v1 that's parallel to v2. Now, v1 and v2 are linearly independent, so that they're not parallel, so that there's some component of v1 that's also perpendicular to v2, a non-zero component that's perpendicular to v2. And we get this vector, which I'll call v1 perpendicular, by subtracting this vector projection from v1, because the vector projection plus this red vector equals v1. It follows that this red vector is v1 minus this projection. Okay, well, our projection is v1 dot v2 over magnitude of v2 multiplied by the unit vector v2 over magnitude of v2. That's the projection of v1 on v2. As I said before, this projection plus the v1 perpendicular has to equal v1, and it follows that v1 perpendicular is v1 minus the projection. Okay, well, we can easily calculate that. In this case, v2 over magnitude of v2 is 0.6.8 because v2 is the vector 3, 4. So the magnitude of this vector is 5. Divide by 5, we get 0.6.8. Then v1 dot v2 over magnitude of v2 is what? Well, it's 2, 3 dotted with 0.6.8, and that's 3.6, as you can verify by simple calculation. So that in the picture, the magnitude of v1 turns out to be the square root of 2 squared plus 3 squared, which is square root of 13, between 3 and 4. And now I'm a little suspicious of my numbers over here, because it's 13, closer to 4 than 3. It's not much different than 3.6. These vectors aren't that far apart. Anyhow, you got V1 dotted with V2 divided by the magnitude of V2 gives you the length of this purple line. And then when multiplied by V2 over magnitude of V2, we get our projection. So we take the dot product here, which is 3.6, we multiply it by the 0.6, 0.8 vector, and we get 2.16, 2.88. Okay, that's the projection of this vector onto this one. Then our V1 perpendicular is obtained by subtracting this projection vector from V1. So we do that, and it's easy to do. We get negative 0.16, 0.12. Then it follows that this negative 0.16, 0.1234 is an orthogonal basis. Why is it orthogonal? Because V1 perpendicular, this vector, is perpendicular to the V2 vector, as follows from this whole geometry. Okay, that's an orthogonal basis, and if we take this vector divided by its magnitude here, and this vector divided by its magnitude here, what do we get? Okay, well, negative 0.16, 0.12 divided by that magnitude, and you can verify this, is just negative 0.8, 0.6, and 3/4 divided by its magnitude is 0.6, 0.8. This turns out to be the same basis that we had here, simply because one of our vectors was equal to one of these vectors. Okay, now follows then the V1 perpendicular V2 is what we call an orthogonal basis, and V1 perpendicular divided by magnitude of V1 perpendicular being a unit vector, V2 divided by magnitude of V2 being a perpendicular vector, we have an orthonormal basis.